Hello everyone. Today I am going to give today I am going to give introduction about the group theory which comes under the discrete mathematics. I am Amit Kumar, assistant professor in IT department. So today I am going to give you a lecture on group theory. What happens in the group theory? What are the keywords of the group theory? What are cosets? What are subgroups? What are monoid? What are semi group? What are groupoid? All the things I am going to explain here in today's lecture. So in this, first, what is group theory? Group theory, the study of algebraic structure with a single operation. Okay, this means a study of if there is a study of a algebraic structure, right now I'm saying that one. Okay, if we have so many groups, like a group of boys, group of herds, group of boys, so these all come under the group theory, but study of algebraic structures with a single operation. And a group is a set of equipped with a binary operation that satisfied four properties. Group have the four properties: closure, associative, identity, and inverse. So this is a group. Here it is a set elements. This is a group. So these groups has to satisfy closure, associative, inverse, and identity element. What are the closure property? The closure property states that if we do any operation with the set, the elements comes under this set only. Like if this is a set elements, if I am saying the E, A, B, C. So if we E, A, B, C, E, A, B, C. So if the elements comes, like I am assuming only, I am not giving any operation. If there is any operation, this is star mark, and if there is any operation comes under this one, like I am going to give an operation E plus like I am going to give an operation on A. I am going to give an operation on A plus B. Okay, A star B is equals to A plus B. So the operation should be plus sign. So the elements are A, B, C. Okay, then E, A, B, C. So the elements comes under E plus E, E plus A plus E. Okay, B plus C, and C plus C. So these all elements comes under this set. So this is are the closure property. Now the associative properties state that A star B star C is equals to A star B star C. This state the associative property. The inverse property: if any element present A, then it having the inverse of that one. Means B is equals to A inverse. B should be the inverse of A. Okay, and the identity element, there are two types of identity: left identity and right identity. So the left identity state that A into E is equals to E. Okay, and E into A equals to E. This is the identity, sorry, A. Okay, this is the identity element. This is the left identity, and this is the right identity of that one. So in the group theory, if these four properties satisfied with this one, then we can say that this is a group. Okay, next, the definition of a group: a set, as I have told you before, a set of G with a binary operation star means, or a dot, you can say anything, star or dot, satisfying a closure, associative, identity, and inverse. As I have told you before, that closure tells that A comma B belongs to G. If A comma B belongs to G, then A dot B belongs to G. Associative: A dot B dot C is equals to A dot B dot C. Okay, next, identity elements tell us if for every element E belongs to G such that A into E is equals to E, or E dot A equals to A, means A dot E is equals to A, or E dot A equals to A. as I have told you in the previous slide. Okay, what is the inverse? If such that all element belongs to G, for every A belongs, A into A inverse equals to A into A inverse belongs to E. This is the identity. Okay, this is the group definition. Now there are one of the element I can say abelian group. Here in the previous slide, just give me a minute. In the previous slide, this is the definition of a group, but if I include only one property, fifth property, that is commutative, means A dot B is equals to B dot A for all AB belongs to G. Okay, if this fifth one, if this fifth property is satisfying with this, then this set of fifth property is called as abelian group. Okay, and as I have told you before that I have to explain the groupoid, monoid, semigroup. So the groupoid, it having the two property, closure and associative. If we have the three property, closure, associative and identity, then commutative, then it is a monoid, and the semi is if we include the inverse property only. Okay, these five property divided into three parts, and these three parts are told as a groupoid, monoid or semigroup. Okay, now the next part, example of a group, Z comma plus, it comes under the integer under addition, R plus comma star positive real under multiplication, S3 dot 0 permutation of three elements, because here it is a 3. Okay, these are the examples of the group. Now as we have read up to here, what is group, what is abelian group, what are the properties of the group? There are four property for the group. What are they? Closure, associative, inverse and identity. And if we include only the commutative property in the group, then it is called as an abelian group. Okay, now for these five properties distributed into three parts, and these three parts are called as groupoid, monoid and semigroup. So these three parts include, like if we have the closure with the associative, it is a groupoid, closure with the associative with commutative, this is a monoid, and if we include closure with the associative with the inverse or identity, we can say as semi. Okay, up to here we have read what is the group, what are the abelian group. Okay, next, what are subgroup? A subgroup H of G that forms a group under the same operation must satisfy H is not belongs to phi, closure under operations and closure under inverse. Okay, means the subgroup is saying that we have the element of that one, it present in the group only, but they have some operations. Like I am giving, it is a group, like this is a group G, the element are A, E, A, B, C, D and F. These are the elements and is present in the group. If the element E, A, B is present, then this is the subgroup, and that H belongs to G. Okay, this H belongs to G, means the elements present in the subgroup, the element is in that group only. If the elements are in the group and the element present in the subgroup, then it is called as a subgroup, because and it's come under all the operations because it is a subgroup. Like I am giving an example of the diagram. This is a group, as I am taking, this is a whole group of the element, and this is a part that is known as subgroup. Means all the element of the subgroup is belongs to the group, but not all the elements of the group is belongs to the subgroup. There is some certain conditions over there. Okay, we have to satisfy, but here it is not mandatory that we have to give an example or all this. We can take any randomly example that what is subgroup and what is group. Next, examples of the subgroups, as I am taking even in 2z and comma plus, means even integer under addition and q plus into then positive rational under multiplicative. So the group has the element, as I have created a group of 3, so E 1 2 1 3 2 3 1 2 3 1 3 2, and the subgroup is E and 1 2. So this element 1 2 and this one, this is comes under the subgroup. Okay, next another is cyclic group. Cyclic group, a group generated by a single element G, means cyclic group is saying that if we start from any of this one, we can come under that. The starting and ending positions are the same as we are saying, and here are the, in the cyclic group there are the generators. So G, where G to the power n, where n belongs to integer numbers. So here is the generators G1, G2, then G3, G4 dot G, as this E is identity element. If we perform any mod n operation, then it comes under this, and if we operate any no operation, then it's come under the elements, that is identity element. Okay, example of the cyclic group: Z plus generated by 1, and second one 1 minus 1 I minus I under multiplicative generators generated by I. Like I am giving an example what I am doing. This is the multiplicative. Okay, so I 1 minus 1 I minus I, 1 minus 1 I minus I. Okay, so if we have any operation according to this, we are finding that the generators are identity elements, and we can go from the G0 to Gn minus 1. Okay, the properties of the cyclic group. Every cyclic group is a abelian. As I have told, what is abelian? We have the 5 properties that we have to satisfy with that abelian group. Order of a cyclic group is equal to order of the generator. What are the order of the generator? As I am going to discuss right now. What are the cyclic group? This is the cyclic group which is generated by the G. Okay, what is abelian group? As we have the some property, and we have the unique order, like unique order, and we have given any order of that one. So we have to find the subgroups are the cyclic, or subgroups are in the form of subgroup, and power of G is every element, means G to the power k. Here it means G to the power k. Next, what are the COSETS? This is the important concept in the group theory, because as we have known what is the group, what is the subgroup, and what is the abelian groups, but what are the COSETS? In the COSETS are tell us if H is a subgroup of G, the left coset is R, AH is equals to AH, and H belongs to H, means the left coset is equal to right coset. And here the left coset and right cosets are telling us that one element is from the group and one element is from the subgroup. That is known as the coset, means this H is the subgroup, and A element from the group. So it is the combination of group with the subgroup. Okay, this is the group E, A, B, C, D, G, H, and this is the E, A, B, and the left coset is G, H, means left coset would be the G, G, A, G, B, and H, A. Right coset H, H, A, H, B, means we can say anything, but one element is from this group and one element from the subgroup. That is known as the coset. Okay, next, the examples of coset as I am taking here. G means the group is Z, means set of integers, and H to Z. So the left coset as I have took from in minus infinity to plus infinity, and also here. So as I am taking the group is set of integers, so minus 3, minus 2, minus 1, 0, 1, 2, 3, and all this one. So subgroup would be, I am taking 2, means the multiplication of 2. So minus 4, minus 2, 0, 2, 4, and here is 6, 8. We can take anything. So the left coset would be 1 plus H is equals to, we are adding that one, minus 3, minus 1, 1, 3, 5, and all this. These are the examples of the left coset. Now, what are the normal subgroup? There are types of varieties of subgroup. So first is coming as, and it is important for the equative, that what is the normal subgroup. The normal subgroup is the H is normal if small g and H is equals to Hg. Here also is saying that this is the left coset is equals to right coset. This is known as the normal subgroup also. So the elements of the G, for all elements E, A, B, C, D, F, G, H, these are in the groups, and E, A, B is the subgroup. So both the elements are present, means if the elements E, A, B and E, A, B are present, then it is called as the normal subgroup. Okay. Now I am going to give an example of normal subgroup, that is center of G is equal to G belongs to group, small g belongs to group, where Gx equals to Xg for all X belongs to G. Here you are saying that G is a universal set. Universal set, it belongs to all the elements present in the set. Okay. Now we are taking some operation, closed under operation E, A, B, C, D, E, F, G, and the subgroup is E, A, B, also form as a group. So this is the example of subgroup that E, A, B is the left coset is equals to right coset, then it is a normal of this normal subgroup. Now next concept is coming as a group homomorphism. What is homomorphism? It means a function. Here we are comparing with the function that function phi belongs to G to H. G means group, H means subgroup, that preserve structure that phi A dot B is equals to phi A dot B for all B and C. This is the group operation. This is the another group operation. E, A, B, C in this group, and E dash F, we are taking the functions of that one, F, B, and this one. And if this property satisfying with any group, then the group is called as the homomorphism of that group. Like F A dot B is equals to F A dot star F B. If there is a two operation, dot and star, if dot and star has the two operation and that this satisfied with this property, if the group having and the another group having, then both the groups are the homomorphism. Okay, both the groups are the homomorphism. The example as I am taking, this is the group G with the operation dot, and this is the group H with the operation star. And if this property satisfied, means E have the function E dash, A have the function A, B have the function B, and C have the function C. If they are mapped with each other with this operation, then it is known as the homomorphism of the group. Next, what are the application of the group theory? The group theories of the applications are cryptography, which we use, quantum physics, computer science as in data structure, chemistry and molecular structures that are in symmetry in molecules, robotics in AI, that are transformation in the group. There are various applications of the group theory. Now in this, there are the two main basics concepts over there, ring and field in the abstract algebra. So what are the rings and what are the fields? So what are the rings? A ring is a set with two binary operation, addition and multiplication, where addition forms an abelian group, multiplication is associative, and distributive law holds. Means we have the three properties in the group theory. If these three properties will hold, then we can say that this forms as a ring. Means addition form, we have two binary operations. What are they? First is addition and second is multiplication. So if the addition form is an abelian group and multiplication is an associative and distributive law also holds, then it is a ring. And what are the examples of ring? Integer, that is Z plus into matrices, if we are taking matrix in plus and into polynomials, that is polynomials plus and star, modulo ring, Z and plus and multiply. These are the some examples of the ring which holds these three properties. If addition, if we perform an addition with that one, that addition should be an abelian group. If we do the multiplicative, then it multiplicative should be the associative, and if we have to do the distributive law, then it should be controlled over the distributive law. These are the properties of the examples of the rings. Now the properties of the rings, as I have told you, associative, A star B star C is equals to A star B star C. Distributive law, A plus B plus C is equals to AB plus AC. Commutative law is saying that AB is equals to BA, and additive identity, that is A plus 0 is equals to A. These are the properties of the ring where we have to satisfy with all this. If the group are satisfying these properties, they comes under the ring. Now what are the fields? A field is a ring where every non-zero element has a multiplicative inverse. Addition and multiplications are commutative, has both additive and multiplicative identity, have the identities. Examples: real numbers, rational numbers, complex numbers, and all these are comes under the field. What are the examples of the field? Rational numbers, real numbers, complex numbers, and finite fields. As I have took, plus and star has the two operations with that we have to perform and we have to satisfy for this one. Additive and multiplicative are commutative, has both additive and multiplicative have their identities. Okay, these two properties they have to hold. Now next, what are the application of the rings and field? cryptography, where ecliptic curve cryptography is having to be used. In the computer science, error detection codes are going to be used. In physics, quantum mechanism, symmetric groups are having used. In engineering, control system and signal processing are going to be used for the rings and fields. What are the verses of rings and fields are there? Rings and fields are fundamental in abstract algebra and have wide applications. Rings generalize number systems with two operations. Okay, rings have the generalized number with the two operations. Field extend rings by requiring multiplicative inverse used in the cryptographic, physics and computer science. Okay, these are the topics where it comes under the group theory, and it is the basics topics as I have took, and I have completed all the topics from the group theory. But there are many more things in the group theory which we are reading and teaching, and all the things from the group. There are more number of this group theory, and group theory comes under, group theory is one of the subject also in the computer science, but in this university it can't get that one, so it is in the subject also in the part of this discrete, so we are going to be used. Okay, thank you.